7.4 is all about least squares regression. So it's basically the next part in helping you have the line of best fit and the best one that you can possibly get. So what we learned in the last section was basically a way that you could eyeball where your best line would work. In this case, you're going to have technology help you to find the line of best fit. Based off of what's called the least squares regression. Before we get into that, it's important to know what residual means. So it's basically the vertical distance of the gap between the line that you drew and the point that's furthest away. In this case, you can kind of see the distance of this little point here at the bottom compared to our line. It's a very large gap for that point. So if that's a line that we eyeballed, drawing it in there, we might be able to find a better line of best fit using technology. So what we're going to do is we're going to do a linear regression, or the least squares regression. It's basically so that you get the smallest possible square of the residual. So we don't want, see how all these little squares are created there in light pink here? We want the smallest number of those squares as we can, or the smallest area. So what we're going to do is going to have technology help us figure out where does that happen. Okay, so in this case, we're going to go straight to example 5. What the regression line feature in your calculator is going to give you is it's going to give you the slope, which is your gradient, and then it's going to give you the b value, which is your y-intercept. Okay, so it's like y equals mx plus b, and basically you're going to take the two pieces and put them into an equation. So right here we have example 5. It says, as a car's tires become worn, it uses more fuel to travel the same distance. This table shows the age of the tires versus the kilometer of the car is traveling on 1 liter of diesel. So we have 6 numbers, 1 through 6, and then we also have the kilometers that we are driving, kilometers per liter. So what we're going to do, I'm going to show you this on DESMOS. The way you find it on a graphing calculator is very similar to doing standard deviation. You'll type it in, and when you go to calc, you'll be able to find the linear regression app really easily. So I'm going to actually show this one on DESMOS because it's a little bit more challenging. So I'm going to type in all this information into DESMOS, into the table, and then I'm going to use that to help me find all the pieces that I need. Okay, so let's go over to DESMOS. So when you're in DESMOS, you're starting off on a blank screen. We're going to go ahead and put in our table. And we had 1, 2, 3, 4, 5, and 6. Oops. 6 on the left side. And then we had 20, 18.5, 17.4, 15.6. As you can see, while you are typing these, they are popping up on your screen, which is what I love about DESMOS. We don't have to worry about hitting the graphing button. So there's all our points. And we can zoom in as we want to zoom in. There we go. So normally when you were asked to find the line of best fit, you would go ahead and just draw a line where you think it would hit those points. I'm going to go ahead and use DESMOS to help me find that. So what I'm going to do, now we got the points on there. Now, if you're on a graphing calculator, you're just going to go over to the stat button and over to calc, and you'll be able to find the linear regression button, and it'll give you the same features, but it's a little bit more challenging. We're going to go ahead and add an expression. So go to the plus sign, and we're going to add this expression in here. So what we're going to do is we're going to type in y equals mx plus b. That's what we're going to type. However, you need to match the variables that are on your table. So see how it says x1 and y1? That's what I have to put instead of x and y. So we're going to put y1, and when you do a subscript, you have to do an underscore, and that makes a subscript. So you can see that the little cursor went down, or she'll get an error. Okay. Also, you cannot put the equal sign. You have to put the tilde, which is a little squiggly, like that, a little squiggle. And then we're going to write mx plus b, but instead of x, we're going to write x1. So oops, we're still in subscript. Tilde mx, and then you can kind of start seeing stuff pop up when you're typing. So make sure you put x1 with a subscript, and then plus b. So tilde instead of an equal sign, and then you need a subscript of 1 with the underscore. So what we have here, it already gave us our some stats here. It drew the line on there for us, and then it also gave us the slope and the y-intercept. So that's going to be the line that the graph is asking for. And that's pretty much it. So that is the line of best fit, and we don't have to worry about eyeballing it. Okay, so what we're going to do is we're going to jump back over to the question, and they actually have the answer down here below. So we wrote down the regression equation. So take your slope and y-intercept and put them into your equation. So y equals negative 1.34 x plus 21.27. That'll be your line of regression. You just have to put them into the equation. Okay, and then it's basically saying interpret the meaning of what the slope means, and then also your y-intercept. So y-intercept here is the 21.273. It's basically when your car is at 0 liters of gas, I think, and you have brand new tires. Basically, you can travel 21.3 on 1 liter of diesel. Okay. The slope basically means that every year the car travels, your tires basically make your miles per gallon or miles per liter, or in this case, kilometers per liter, go down 1.34 for every year you have the car. Okay. The last piece says use the equation of the regression line to estimate how, or the distance the car would have traveled on 1 liter of diesel when the tires are 3.5 years old. So basically what you're doing here is you're plugging in 3.5 for M, and then you're calculating it. Okay. Because there's no 3.5 anywhere on here, you're basically going to get a number between 17.4 and 15.6. Use your equation to solve what it's asking for. So you're just plugging in 3.5, not 3.5. 3.5, and then you get 16.6 for your answer there.